Hello, Hornets. Today we're going to be talking about the next step in our flowchart, and that's talking about certain series that we already know. For example, we already know that if we have a series such as n approaching 1 to infinity, and let's go 2n plus 3, you'll notice that this is arithmetic. And because it's arithmetic, as we take our limit, as n approaches infinity for 2n plus 3, we get infinity, and therefore this will diverge. Now, you'll notice I started with the arithmetic series. Arithmetic series diverge simply because they do not have a limit as n approaches infinity equaling 0. And this is always the case. So we can now pretty much look for this as a characteristic. If we see an arithmetic series, we throw it away as divergent. But then that does bring us to the geometric series. For example, if I take the series as n starts at 1 and moves to infinity, and I have 1 over 3 to the nth power, I'm now looking at a geometric series. And in this geometric series, we know that we can find the limit at infinity. This is using our a sub 1 divided by 1 minus r. And this applies only because the rule a sub n has an absolute value that is less than 1. So if I then do this, I know that a sub 1 is 1/3, and r is also 1/3, allowing me to find 1/3 divided by 1 minus 1/3, and you'll notice I end up having 1/3 times the reciprocal of 2/3, which is 3/2, and I end up having a sum that is 1/2. So not only do I know that it is going to converge because A, it is geometric, and B, the absolute value of the ratio or rule is less than 1. We know this from our pre-calculus and from Algebra 2. So we now have two situations that we can guarantee without having anything to worry about. The first is that if I have an arithmetic series, I know I have divergence all the time. If I have a geometric series, then I will have convergence if the ratio of the geometric series is less than 1 for its absolute value. But I know it will diverge if the ratio is greater than 1. This brings us to our third situation that we're going to be talking about today. And the third situation is a telescoping series. Now, telescoping series are series that decompose. For example, if I take a summation, and I have it starting going from 1 to infinity, and I look at 6 over n times n plus 3. We can all clearly see that this is going to decompose. Not only that, but it will decompose into the following series. Now, I've already done all of the work for this, and I would expect everybody to go and review decomposition of fractions if you are unsuccessful or unaware of what to do. So I've gone through and I've already found my A and B, and I've broken it down. Now you'll notice this series has two pieces, both of which are harmonic in nature, and we will be talking about the general form of a harmonic series shortly. But you'll notice if I put in a 1, I end up getting 2 minus 2 over 4, which is really 2 minus 1/2. If I then go n equal, and this was with n equals 1, keep that in mind, we yielded that. If n equals 2, we're going to have 1 minus 2/5. If n equals 3, we're going to end up with 2/3 minus 1/3, n equals 4. You'll notice I'm just constructing my series 1/2 minus 2/7. N equals 5. I end up with 2/5 minus 1/4. And I'm going to do one more just so that we can see it. And here I'm going to have 1/3 minus 2/9. Now I'm going to put this together. This series is 2 minus 1/2 plus 1 minus 2/5 plus 2/3 minus 1/3 plus 1/2 minus 2/7 plus 2/5 minus 1/4 plus 1/3 minus 2/9, and this continues infinitely. But I want you to notice a couple of things. See how this 2/5 right here is positive? This 2/5 right here is negative? They cancel. Here's a 1/2, and it cancels with a 1/2. Here's a 2/3, and here's a 1/3. Let's go ahead and get rid of the 1/3. It looks like that's canceling. And now, as I look at this, I notice that there are certain things that don't cancel, okay? And the certain things that don't cancel, there went my lights, are 2 plus 1 plus 2/3. Now, all the way at the other end, we have n minus 1, n minus 2, etc. So if I were to find n minus 2 and work my way to n, I'm going to get 1 over n minus 2 minus 1 over n. N minus 1 is 1 over n minus 1 minus 1 over n plus 1. And then when I have n, I have 1 over n minus 1 over n plus 2. Now, if I'm looking at n approaching infinity with each of these, you'll notice it doesn't matter which terms remain. Based upon which terms remain or don't get canceled, I can clearly see that the limit at infinity is still equal to 0, and I will be adding or subtracting 0 all the way at the end of infinity, leaving me only with the 3 2/3 equaling my sum. Now, telescoping series always do this. They always have a sum, and we can find that sum by expanding out our series. If by chance we encounter one of the very few telescoping series that do not converge for some specific reason, it'll become obvious when we expand it out and try to cancel out terms. The terms won't cancel, and I will end up seeing very clearly that I have a divergence. This will also be shown at the end when I plug in the values of infinity for things like 1 over n plus 2, etc. We'll end up having something that causes a divergence, or something that equals infinity. So we now have 3 series that we can guarantee. We have the arithmetic, which will always diverge. We have the geometric, which will converge if the ratio is between 0 and 1, or the absolute value of the ratio is less than 1. Diverge if the absolute value of the ratio is greater than 1. And now we have our telescoping series that can be broken down into decomposition and having 2 basic harmonic terms. And all of these are pretty straightforward to see. Thank you very much, Hornets. In my next video, I'm going to go over some examples where we can take a look and determine convergence or divergence for ourselves as we look at various pieces. Thank you very much, and have an excellent day.